Hi, I'm Nir, and I'm happy to be here. After COVID-19, it's a really big pleasure being back again. What I want to talk about is, this is the, yes. What I want to talk about are two things. Basically, I want to follow what Professor Happer did in his talk that ended just a minute ago. And I want to take that and to basically discuss two things. The first thing, okay, this is basically the summary of what I'm going to say, so afterwards you can fall asleep. Just remember what is written on this slide. The first thing I want to talk about is the fact that the sun has a large effect on climate. And the other thing is that climate sensitivity, which is what Professor Happer was just talking about, is on the low side. So we'll want to discuss these 2 points. Now, these 2 points, I think, are probably the most important questions in climate science because they help us understand what has been going on with our climate over the past century, and it will help us, or it helps us understand what the future climate change is going to be. And I also note that it's related to the talk of my colleague who just disappeared, which is on the effect of cosmic rays on climate, and that's basically to understand how is it that the sun has such a large effect on climates. Okay, so I'm going to set the stage. I'm going to show you, I'm trying to convince you that the sun has a large effect on climate, and hopefully you'll be convinced. The exact link is going to be in the next talk. Okay, so let's begin with the sun. The sun has a large effect on climate, and here it goes. So first of all, we have to realize that the sun changes its activity. We can see that, for example, in the number of sunspots that it has. This change in activity manifests itself in the change in the solar wind, in the amount of UV that outputs from the sun, and so forth. At the bottom right, you can see what the sun looks like in hard UV between when it's active and when it's inactive. And it turns out that these changes in activity translate into large changes in the climate here on Earth, and we'll see how that comes about. This is just shows you, by the way, you see here the top, the regions outside the sunspots, they look like this kind of creamy soup. This is just the convection that Professor Happer was talking about before, because the outer parts of the sun are convective, like Earth. Okay, so before showing you that the sun has a large effect on climate, let's see what the IPCC tells us is the effect of the sun. If you open the reports of the sun, such as the last one, you will see a graph like this one, which tells you what is the changes in the total solar irradiance, which you can translate into changes as the change in the energy budget here on Earth per meter squared. How many watts does the solar activity translate into? And you can see that the changes in solar activity translate into changes of about 0.1 watt per square meter on the surface of the Earth. And we have to compare that to the 240 watts per square meter, which we get from the sun, or reach the surface from the sun anyhow. So the changes in the solar irradiance are minuscule, and because they're minuscule, they cannot really produce large effects in the climate, large effects in the temperature. And this is why, if you sift through the IPCC reports, you'll see things like this graph, where they claim that the contribution of solar activity into changes in the global temperature over the 20th century is close to zero, or consistent with zero. Here, if you didn't see that before. Okay, so you can open, this is from the previous IPCC report. The last report doesn't have a graph as nice as this one. This is the contribution of the different gases that, these are the greenhouse gases, these are effects of aerosols and so forth if you open that report, the previous report, you'll see that they claim that the contribution that the sun has into changes in the energy budget over the 20th century, or since the Industrial Revolution, is very, very small. And I'm going to try to convince you that it has to be very large. Okay. So how do we see that the sun has a large effect on climate? And the answer is yes, and we can see that on different timescales, and this is probably one of the nicest graphs I know. Here at the top, you can see a reconstruction of the solar activity. It's basically the amount of carbon-14 which is produced in the top part of the atmosphere by high energy particles coming from outside the solar system. But when the sun is more active and it has a stronger solar wind, less of these particles can reach the atmosphere and you get less carbon-14. So when you have more carbon-14, it means that the sun is less active, and you can read that by looking at the amount of carbon-14 you have in the tree rings. At the bottom, you have the isotope ratio of oxygen 18 to oxygen 16. Oxygen 18 is heavier than oxygen 16, so the evaporation rate is temperature is different for the different isotopes, but it depends on the temperature. So in this case, what you have here is basically a proxy of the temperature of the Indian Ocean, because this is isotope ratios from stalagmites in a cave in Oman in the southern Arabian Peninsula. Okay, so obviously, I don't know if you noticed, I hope you did, that there is a nice correlation between the two. Do you see the correlation? Yeah, I guess so. So obviously it tells you that solar activity affects the climate, or maybe vice versa. Maybe what we're affecting the climate affects solar activity. Right? Makes sense, right? Okay. It's a joke, of course. This is from the northern part of the Atlantic. It's something similar. We can see, we can take ice cores, sorry, not ice cores, we can take ocean sea cores from the ocean sea floor, and we can measure when was there colder epochs, because when it's colder, dust which settles on ice can float further south, and when it melts, it releases its ice onto more southerly latitudes. So here at the top, you have a correlation again between solar activity as mimicked, as proxied by the carbon-14, and in black you have the seafloor records, which shows you whether it was cold or warm in the northern Atlantic. So we can see that in different places on Earth, there are large correlations between solar activity and climate variations. Okay. By the way, the IPCC tells us, oh, the sun may have an effect, but it's local, like there's no global effect. So you can see it locally here, and locally there, and locally over there, and locally everywhere. Okay. Now, what we see now was on timescales of about several thousand years, and it's hard to quantify how large the effect actually is. However, you can look on shorter timescales and quantify the changes in the solar radiative forcing by looking at the amount of heat that goes into the oceans. So what you see here is the solar activity in red, and in blue you see the change in the sea level of the oceans. And on short timescales, most of the change of the sea level is due to absorption of heat by the ocean. So the oceans thermally expand. So basically you can use the tide gauges to quantify the amount of heat that goes into the oceans over the solar cycle and see that the effect that the sun has on climate is very large. How large? It's more than 1 watt per square meter change between when the sun is less active or more active. And this you should compare to the 0.1 watt, which I showed you before, or the something like 1 or 1.5 watts, which is the change in the energy budget associated with the CO2. Okay, so the sun has a large effect. You can quantify it. You can see that in more data sets if you didn't believe the previous one. Here you have the satellite data, with the dots. This is satellite altimetry measuring the height of the oceans. And you can see that if you use a model which includes the solar activity and the El Nino Southern Oscillation, you can explain almost all the change in the sea level, minus the long linear trend, which is associated with melting of ice. But all the short-term variations in the sea level are due to solar activity and El Nino. So you can, with that, again, quantify the effect that the sun has and see that it's large. And if this wasn't sufficient, you can see that with the ocean heat content data. There are floats with temperature gauges which are measuring the temperature at different depths. So you can see how much heat the ocean stores, and you can differentiate it. And when you differentiate it, you find that, okay, this is solar activity again. You can see the solar cycle where the sun flips its magnetic poles. And in the top, you can see that every time the sun was more active, heat was going into the oceans and vice versa. So also the total, another independent record shows you exactly the same. So the sun has a large effect on climate. What does it mean? It means okay, so these are the different records. Some of them I showed you, like the tide gauge record or the satellite altimetry or the ocean heat content, but you have additional records with which you can quantify the effects that the sun have, and they're all consistent with a large variation over the solar cycle. And this should be compared to the size of the variations that you would expect from just the changes in the total solar irradiance. So this difference tells you that there should be some kind of mechanism that should explain why the sun has such a large effect on climate. And this is exactly what you're going to hear from Professor Svensmark in the next talk. He disappeared. I don't know where he is. Okay. Because that's a mechanism. Today we know exactly what this mechanism is and how it operates. Okay. What does it mean towards to the understanding of the 20th century warming? We see that over the 20th century, solar activity increased, and therefore, if the sun has a large effect on the climate, it means that some of the warming should be attributed to the fact that solar activity increased. If you go back to the plot I showed you before, instead of having this small contribution by the sun, taking this, the increase in solar activity and taking the forcing that we measure, we can calculate what the contribution should be, and it should be this. Okay, this is something that the IPCC models are completely missing. Okay, so the sun has a large effect on climate. And the other thing I want to talk about a little is the climate sensitivity. How much is the temperature on Earth supposed to change if we, for example, double the amount of CO2? These questions are related to each other because if the climate sensitivity, so why is it important? If the total radiative forcing over the 20th century is large, because not only are there contributions from greenhouse gases, but there's also a large contribution from the sun, it means that in order to explain the same type of warming, we need a smaller sensitivity. While if we are missing a large radiative forcing, we will need models which are very sensitive in order to explain what's going on. So we have to understand both things together if we want to understand what has been going on over the 20th century. So we talked about solar activity, and now I want to say something about climate sensitivity. So climate sensitivity is, here I ripped a graph from Professor Happer's talk. It was very fast. I took it from you. No, just kidding. I ripped it from a previous lecture that you gave. So we saw, or we understand from Professor Happer's talk, what the greenhouse effect is. It is a change in the energy budget associated with the fact that we increase the amount of infrared absorption in the atmosphere, and therefore we reduce the emission going back to space. And if we reduce the emission going back to space, and we want to be in equilibrium with the amount of radiation that we get from the sun, then we need to warm the surface. Okay, so we need to warm the surface in order to reach this equilibrium. Now, if everything else in the atmosphere should have been kept constant, then this heating should be around 1 degree increase per CO2 doubling. Okay? For comparison, the IPCC, of course, tells us that it's much more, and we'll see in a second why. Now, the question is why, maybe I'll go back again. Okay. This is the temperature increase, sorry. This is the temperature increase if everything else in the atmosphere stays the same. However, if you warm the oceans, you might evaporate more water. And water is an excellent greenhouse gas. And if you have more water vapor in the atmosphere, you can also have more clouds, and the clouds can warm and they can cool. They can operate as a blanket, or they can reflect some of the sunlight. So there are a lot of processes that can take place which would modify by how much the temperature of the Earth would change when you change the amount of CO2. Now, the big question is what will the clouds be doing? And I think one of the nicest graphs I've seen ever is from a paper which is already 30 years old. And that shows us at the time what the climate sensitivity is of the different models. So this is if we double the amount of CO2, the temperature will increase by, say, 3 degrees. As a function of what is the radiative feedback that the clouds impose. You see that if it's positive, if you change the surface temperature by 1 degree and the clouds will want to heat the Earth even more, then you get models which are very sensitive to changes in to doubling the amount of CO2. Whereas if the feedback through clouds is negative, if the clouds, if we warm the surface by, say, 1 degree, and you get that the energy balance is now negative, that the clouds want to cool the Earth, then you get that it's a negative feedback which wants to give you a lower sensitivity. And given that the models all sit close to a line, and this is the free parameter that you have, it shows you that cloud feedback is basically the largest uncertainty in the climate models. And if you don't know what the cloud feedback is, then the models operate in what's called, what's in computers is called GIGO. It's garbage in, garbage out. The recipe that you use to describe the cloud cover is going to describe the change in the, or the climate sensitivity. Okay, so if you open the last IPCC report, they'll show you that they think that if you double the amount of CO2, the temperature should change by anywhere between this value and this value, between 1.5 and 4.5 degrees. And this dates back to a federal committee that convened in the US some 40 years ago. And this stayed basically the same over 40 years, even though we invested billions of dollars or Deutsche Mark or euros or whatever in order to understand climate better. So this is from the last report. Basically, we still have a large uncertainty. And what they tell us is that given that we can have models which are very sensitive to changes in the energy budget, we could be warming the planet at a hysteric rate, and therefore we might be heading ourselves towards a catastrophe. What I want to show you is that it should be somewhere on the low side. So basically, what you heard in Happer's talk was a discussion of what the change in energy budget is when you double the, for example, the amount of CO2, and by how much the temperature should change if you just differentiate Planck's formula. And that would give you a sensitivity which is around 1 degree increase per CO2 doubling. However, this change of energy budget could be associated with a positive energy budget, at least according to the IPCC, due to the water vapor in the atmosphere or change in the lapse rate, or in the long term, you could be causing the Earth to be less wide or reflect less of the sunlight, so it will warm. And here, this is what they claim is the uncertainty of the cloud cover. So when you add all these 4 things together, you get a climate sensitivity, which is here, which can be anywhere from something which is reasonable to something which is hysteric. I mean, look at it. If you will increase this error bars just by a little bit, you'll already get that it can diverge. The climate system would be unstable, totally unstable, which we know it's not. Okay. So what is the climate sensitivity? What is the value? To answer this question, we can look at different type of methodologies. One would be to compare the change in temperature following a change in energy budget that we can estimate on different timescales, and then multiply by change in energy budget, which is associated with doubling the amount of CO2 to get how much we expect the temperature change to be. And here you see results that you get when you look at the past 500 million years, or the warming from 50 million years ago, or 400 million years ago, or variations over the 11-year solar cycle, or the warming since the last glacial maximum. And what you see is that you get a range of values, but if you add the effect that the sun has and that the cosmic rays have on climate, you get consistently the same result, somewhere between 1 and 2 degree increase per CO2 doubling. So this is on the low side. This is from much more recent work where we compared the temperature over the past 500 million years, that's in black, which is reconstructed by various means, with the contribution that we expect from cosmic rays, from CO2, and from the fact that the sun has been increasing its luminosity over the past 500 million years. You can compare everything together, put it and try to find a good fit. And the good fit gives you a value for what the climate sensitivity should be, which is at the lower range of what the IPCC claims it could be. Namely, models which are very sensitive can be ruled out. This can have some kind of systematic effects because basically on timescales of hundreds of thousands of years, we see that the CO2 and ammonia, and methane change together such that this would be the sensitivity not of CO2 alone, but of CO2 plus the methane that changes with it, which could be like 25% more. So in reality, the sensitivity can be even smaller than that. Okay. Is there any observational evidence which can suggest what the sensitivity is? And the answer is that there are good hints, but it's messy. Here, what you see is the amount of flux going from the surface, not from the surface, from the top of the atmosphere to space as a function of the surface temperature. So each point here corresponds to a surface temperature, an element with a surface temperature of 260 degrees Kelvin, and you see what the emission to space was based on satellite measurements. And you can see that basically everywhere on Earth, you get a very nice linear relation. This is for clear sky. This is when you don't have any clouds. And you see basically that there is a nice relationship that tells you that if you change the temperature of the surface by a given amount, you will change the flux going out. So if you double the amount of CO2 and you change the equilibrium by a given amount, you can estimate by how much the temperature is supposed to change. And this gives you that, that the clear sky sensitivity should be somewhere around here. Namely, if you add this number and this number, and I think possibly this number, but it's tricky, then you will get a sensitivity which is somewhat less than 2 degrees. And that's before the clouds can stabilize it even more. What do the clouds do? This is even trickier. What you see here at the bottom is comparison of changes of the flux going out of the atmosphere as a function of the temperature of the surface of the Earth, or not, this is not the surface, this is the lower part of the atmosphere, it's satellite data. And you see that there is a correlation that when the surface of, when the temperature of the lower atmosphere is higher, the flux going into space, including regions that have clouds, increases, and that tells you what is the feedback. The catch is that if you look not at the changes the flux, the changes in the flux is a function of the changes of the temperature for different months, but you compare one month to another, namely you look at only the short-term changes, you get an even larger correlation. Now the slope is basically this sensitivity. So this gives you this slope and this gives you that slope. Which one of them is correct? I don't know, because it depends on why, what's the mechanism that gave you this behavior. For example, it could be that the temperature of Earth just is floating, like if you don't have any grounding to your electricity, the temperature can be floating. And the reason could be that for the same average global temperature, you can have one region which is warmer and one region which is cooler, and you will get one output of the radiation. And in another situation, you'll have it the opposite, that the first region would be colder and the other region would be warmer, such that you get the same average conditions, but because the second region is is oceanic and more humid, you will get less radiation going out. So this would give you a behavior which tries to destroy this correlation and artificially give you a smaller feedback, cloud feedback, and therefore a larger climate sensitivity. On the other hand, if you have feedbacks which operate on timescale which is longer than a month, then this would be the short-term variability, but it could be that on longer timescales you behave more like this. So I don't know, but my guess is that the observations tell you that the climate sensitivity should be anywhere between significantly less than 1 to somewhat less than 2. But definitely not like 4 or 5. Okay. You can also try to simulate the 20th century and add the contribution that the sun has. And what you do when you allow the sun to have a large effect on the climate, you find that you can explain the behavior of the 20th century much better than you do without it. Here, for example, this is from the last IPCC report. You can see here models that they try to fit, and the temperature and the actual temperature, and you can see large residuals. For example, here in Pinatubo, the models give you that the temperature should have decreased much more than in reality. And that's because the climate models are more sensitive. Okay, so going back to what I said before, standard picture assumes that we only have anthropogenic forcings, or almost only, and therefore you need a high climate sensitivity in order to explain the 20th century warming, and therefore the predicted temperature increase over the 21st century is going to be larger. In reality, you have an additional large forcing, which is the sun, and therefore you need a smaller climate sensitivity to explain what was going on, and therefore you predict lower temperature increase over the 21st century. How much smaller? This is, if we run the same simulations that fit the 20th century, 100 years into the future, with realizations for what the sun would be doing and what volcanoes and such, you get that the temperature increase should be about 0.15 degree per decade. This should be compared to typical IPCC scenarios, which are way higher. Incidentally, if you look at what the warming has been over the past, say, 30 years, you find that it's completely consistent with our predictions and way smaller than what the climate models are giving us. And therefore, what you should do in a decent scientific discipline is understand that these models are wrong and rule them out. But this is not what's happening. Okay, so I will end with the summary I began with. The sun has a large effect on climate, and it explains about half to two-thirds of the warming over the 20th century. Climate sensitivity has to be on the low side. Ballpark around around 1 degree or 1.5 or somewhat less than 2 degrees if you double the amount of CO2. And that means that the warming over the 21st century is going to be benign. And the next talk is going to be an explanation for why, Okay, I'll end with this. The next talk would be why the sun has a large effect on climate. And this is what I think, I'll quote Al Gore quoting Mark Twain, this is why what I think of the current situation, that our ignorance causes us to do things which we shouldn't, basically. Okay, and we'll have the Q&A afterwards, after Henrik's talk.
Well, thank you very much. It's a pleasure to be here. I'm very surprised to see so many people at this conference. I mean, I'm impressed how much it has grown over the years. So, yeah, well, I'm going to talk about the mechanism, and as you can see, it's done in collaboration with Martin Enghoff, who is in my institute, and also NIR, and actually my son has also been involved since 2009, actually, in working with us. So what you see on this picture is more or less what I'm going to talk about today, which is an effect from space on the Earth's climate. And the general idea is that cosmic rays from space, that is out here, we have energetic particles which are accelerated and they enter into the atmosphere. And we have spent more or less a large number of years trying to understand why there should be a connection between these particles entering into the atmosphere and then the Earth's cloud cover. And that's a story I want to tell you. 10 years ago, I would be very uncertain if we had the right idea, but now I think we are getting much more certain that we are on the right path. So I'm going to talk about cosmic rays and clouds and about the physical mechanism between ionization and cloud formation, and then some further empirical evidence in order to show you that there might be such a connection between cosmic rays and clouds. So where do cosmic rays come from? They come from large stars that explode. So these are the cosmic rays we are interested in. Oh, sorry. Do I go back here? Yeah. So when these stars explode, they accelerate particles to enormous energy, and then they enter into the solar system. And when they enter into the solar system, they meet the sun's activity, that is the magnetic activity. So what you see down here is from 1960 to about 2000, and the orange curve here is just the sunspots that you probably have seen so many times. But up here, you see the changes in cosmic rays, and you see when you have a many sunspots, you have a low cosmic ray flux. That's because the shielding is better when the sun is very active. So you have this inverse correlation between the two. Now, when these particles enters into the atmosphere, they actually produce ions. So you see these ions here, and on top of that, because the energies are so high, you produce new isotopes. And one of the isotopes is, for instance, carbon-14. And carbon-14 then goes together with the oxygen molecule and becomes CO2, but it's not slightly heavier form of CO2. It goes into a tree, and then it might end up in a tree rings, as you see here. And if you measure the carbon-12 relative to the carbon-14, you can, from a certain ring, say something about how active the sun was back in time. So the interesting thing is that each time there is a change in cosmic rays, it looks as if there is a change in climate. And this is what we are seeing here. Up here, this is the last 1,000 years, more or less, where you see a temperature curve, where you have the medieval warm period, you have the Little Ice Age, and then you have the modern instrument record. But down here you have the changes. It says in carbon-14, but you can say it's solar activity and cosmic rays. So down here you have more cosmic rays coming in because the solar activity is low. And when you have a high cosmic ray flux, it appears that you have a colder climate, and vice versa. So you see this beautiful correlation, and it's not just in Europe that we have seen that it has a large effect on civilization. This is a work. This is a work it published in Science, and it has to do with the Asian monsoon, where you see here the medieval warm period and the Little Ice Age. And the interesting thing is that each time there is a large change in the monsoon, the dynasty, that is sort of the end, and a new dynasty appears. So it says something about that there is a relationship between culture and these changes in climate. Just to say that it has had significant influence on civilization, these changes. So here I'm trying to quantify, as Nia also did, the effect of solar activity. So here you see the changes in solar activity with the 11-year cycle, and then you see that this ocean expanding. You can see how much heat is going in, and from that you can calculate the forcing from solar activity, and you get a figure that looks something like this, where depending on which data set you are using, you're getting between 1 and 1.5 watt forcing over a solar cycle. So here you see the total solar irradiance. It's almost a factor of 10 too low. So if we are going to explain this, we need an amplification mechanism. So what can the amplification mechanism be? So the idea that we had has to do with clouds, as you can see here in this beautiful animation from a geostationary satellite. So the net effect of clouds is that they cool the atmosphere with between 20 and 30 watts per square meter. So if you have a systematic change in the Earth's cloudiness, you will be able to change the climate on the Earth. So that was sort of the initial idea we had already in 1995. So it goes a long way back, where we produced this type of figure. So this is from 1983 until 2006. And what you see here in the red curve is actually the change in cosmic rays. And you see this solar cycle modulation. And the blue curve, that is changes in low clouds, and it's measured by a whole fleet of satellites. And unfortunately, already here in '94, there was some calibration problem, and we tried to fix it, and we couldn't fix them because now the calibration is completely off. So we cannot sort of give further support to this correlation, but that was the sort of the initial evidence that gave us the idea that maybe cosmic rays are linked to clouds. And the interesting thing here is also that the change that you see in clouds is about 1 to 2%. And if you look at this next figure, you can see that the forcing from 1 to 2% is in the right order of magnitude to explain these observations over the 11-year solar cycle. So if clouds are important, and if cosmic rays are connected to clouds, then the question is what is the mechanism behind this? And in order to understand a little about clouds, we have to look at how you actually form a cloud droplet. And you can see it here. So in order to get a cloud droplet, you have to have a surface on which water vapor can condense. And that is what you call a cloud condensation nuclei. It's typically about 50 nanometer. And what is interesting in this context is that most of these cloud condensation nuclei that we are interested in are over the oceans. And here, these cloud condensation nuclei, this actually start as gas molecules that then condense into a small molecular cluster. And then by taking up more of this gas, and maybe also by collisions, they grow, and that takes about a week, and then they can become cloud condensation nuclei. So the idea that we had was that this ionization here, when you have these charges, they help the stabilization of these small clusters. And by stabilizing them, that means that they don't evaporate so easily, and therefore they might survive and grow to cloud condensation nuclei. So I can show you here in this figure that if you change the cloud condensation nuclei, you are changing the cloud properties. What you see here is a region from a satellite where you have over the oceans, and you see these stripes, and this is where ships have been sailing. And as the ship sails, it sends out a lot of small aerosols that can function as cloud condensation nuclei. So in these stripes, you change the number of cloud condensation nuclei, and you can see it changes the optical properties quite dramatically of the clouds. So that is the general idea. So with these ideas, we could then try and begin to test whether we experimentally could see any of these effects. So we have, over the last 10 years, been involved in a large number of experiments. This is an ongoing experiment at the Technical University in Lyngby in Denmark. We were also involved in the cloud experiment at CERN, and we have also used the accelerator in Aarhus University. At some point, we were even 1.1 kilometer underground in order to avoid cosmic rays. But let me show you one of the first results that we got, which has also been confirmed in the cloud project. So the idea is to look at the formation of small aerosols. So we can, within our chamber, we can add ionization by gamma rays. So by increasing the ionization, this is what we are doing down here, and that is sort of a proxy for cosmic rays. And up here we measure small aerosols, which they're all on the order of 3 nanometers. And you can see that as we increase the ionization, we actually increase the number of small aerosols. And when we did that initially, we thought that, okay, we can simply produce more small aerosols, so now they just have to grow to become cloud condensation nuclei, and that would be the mechanism. But it turns out that that is simply too simple. And the problem is that these small 3 nanometer particles, they have to grow almost 1 million in their mass in order to become cloud condensation nuclei. And there's a big chance that they get lost. They get lost on larger particles. And one of the things that happened was that a number of groups, after we got our results with the experiments, they tried to test it in big models. So they used big numerical models to see if they now put extra in of these small aerosols, will they then grow to cloud condensation nuclei? And that's something you can test in a global model. And here is one model, and this is from 2011. Down here you see the size of the particles. So here you have 1 nanometer, 10 nanometer, and 100 nanometer. And then you put in about 5% extra small aerosols. And then you look at the fate of these small aerosols in the model. And you see as they grow, fewer and fewer survives to cloud condensation nuclei. And if you want to explain the observations we are seeing, we would expect that if you had a few percent here, you would also get a few percent more cloud condensation nuclei. So the models are more or less saying no, that this effect is too small to affect clouds. So one could say that we have experimental, at that time we had experimental evidence that this is going on. We are producing these small aerosols, but these models all said that this is not working in our models, and that has been used to say that this theory, and is still being used to say that this theory is probably dead. However, we spent a number of years doing experiments. This is the experiment in Copenhagen. And what we did was try to test the growth of aerosols experimentally to see if there is an effect. And let me see. Yeah, this is the experiment. So what we did, and this is one of the experimental plots. What you see down here is the time going in hours. So it's about 15 days. And up here, you have the size of particles. So what we are doing is that every 4th hour, we increase the ionization in the chamber, and then after 4 hours, we turn it off, and then we wait 4 hours. So we repeat this in a periodic way. And the whole idea is to see if ionization is helping the growth of particles, of aerosol particles. And the reason that we are doing so many experiments here, it is because we are trying to measure changes in the growth rate that is less than 1%. That's because the experimental conditions are such that we can only measure changes in the growth rate on the order of 1%. It has to do with the amount of sulfuric acid we have in the chamber. So what we do is that we take this experimental run, and then we add them on top of each other, so we get sort of a periodic pattern here. So you have this is when you have gamma rays on, and then you have this when you have gamma rays off, and here you have one profile, and here you have another profile. And this is just for one setting of parameters. We then changed parameters, I mean, just running the experiment, it took more than a year. But what we got was something that actually fitted the theory extremely beautiful. What you see down here is the sulfuric acid that we have in the chamber. I should say that sulfuric acid is something that is produced completely naturally over the oceans, and it comes mainly from algae and sulfur dioxide. But what we see is that we have a very beautiful agreement between the experiments and then this theoretical line. And when we have a lower ionization in the chamber, we also see a fairly nice agreement. So what it's showing is that aerosols are helping the growth of these small particles. So by adding ionization, we can actually accelerate the growth. Let me try to explain you how it works. So if you have an aerosol particle that is supposed to grow, then mostly it will grow from sulfuric acid, and typically over the oceans you will have about 1 million particles or sulfur molecules per cubic centimeter. And the number of ions is only about 1,000. So the ions are also sticking to the aerosols, as is this sulfuric acid. And each time it adds a little mass to the aerosol. And naively, you would think that it has to do with the concentrations that will say how much the growth rate or how important the ions are compared to the neutral growth. And you will say it's just about 0.0% of that order. But it turns out you have to take into account that we are dealing with charges, and when you are dealing with charges, you get these enhanced interactions, and it turns out that the effective because of these interactions, it goes up almost 2 orders of magnitude. And it means that in the atmosphere, you would expect that almost 10% of the growth is due to ions. So that means that if you change the ions, you also change you change the growth rate, and that makes it much more likely that they survive to cloud condensation nuclei. So the idea is that you produce new aerosols with cosmic rays. They help the growth, and then they finally become cloud condensation nuclei, and we have some theory, which I will not go into. And then in the end, they can affect cloud. So that's what the experiment seems to be indicating. Now, all of this is about experiments, and you can imagine that maybe the conditions that we have in the experiment is not really what we have over the oceans and so on. So it turns out it's very fortunate that the sun makes what we call natural experiments with the whole Earth that we can use to test this mechanism. What you see here is this is the sun and this is the Earth, and this is what we call coronal mass ejections, where a lot of plasma is being ejected from the sun. And when you inject this plasma, it's like an umbrella against cosmic rays. So you will typically, if you have a strong event, you can see that you have a large drop in cosmic rays, and then within a week, it goes more or less back as this plasma moves out in interplanetary space. But this is like a natural experiment with the whole Earth, and this we have used extensively recently. What you see here is some of these observations that we did. The red curve is the drop in cosmic rays. This is 15 days before, this is 20 days after. And here you see aerosols dropping down. So when you have fewer cosmic rays, it looks as if there's an effect in the aerosols. And then we have 3 different satellite projects, all with different algorithms and so on, but they all show an effect, and typically about 5 to 7 days after the minimum here. And that's simply the time it takes for aerosols to grow to become cloud condensation nuclei. The latest thing that we have done is to answer the question, does it change the Earth's radiation budget? And we have used the satellite, which is called the CERS, the CERS instrument. And what you see here is 3 graphs. Let's start with this one. What we have here in the, I think the purple line here, that is the drop in cosmic rays. So here you have day 0, and you have 15 days before and 20 days after. And what you're looking at is shortwave, and you can see that there's a very clear drop following strong Phobos decreases. And that's something we see. So it means that less solar radiation is radiated back up until to the instrument. So it means that more energy is going into the Earth's system. If we look at the long wave, and especially low clouds, which is this purple line, I think. No, it's the red line. It's not really changing very much, and that's simply because, yeah, I'll stop in a second. This is simply because of the temperature of low clouds is more or less the same as the surface. So if you have no clouds or you have many clouds, it doesn't make a big difference. But the important thing is that up here you see that the net radiation, you get almost between 2 and 3 watts more energy into the Earth system from a 15% change in the cosmic ray flux. Let me just show you two more slides. What you see here is the interesting thing is that we can actually look where and what clouds are affected by these changes. So this is the average state before the Phobos decrease, and this is after for the shortwave. And you can see that there's enormous amount of areas that are affected. It sort of lights up in yellow. And you can also see it here in the net radiative, that there are these regions, and these regions are mainly over the oceans. So, and if we look at what type of clouds and where they are, so this curve here is where you have low clouds, and you can see the main regions are simply where you have low clouds. So the low clouds are extremely important for this for these changes. So those are the ones that are changing the radiative budget. So let me give a summary of the observations. We have the whole link more or less. So we start with solar activity in the form of coronal mass ejections. Then we get a decrease in cosmic rays at Earth, and we call that day 0. Then we see a decrease in the aerosols 4 to 5 days later. These are relatively large aerosols, otherwise we couldn't observe them. And then we see decrease in clouds 5 to 7 days later, and the energy budget of the Earth changes 5 to 7 days later with about 2 to 3 watts energy. And it's mainly low clouds that are responsible for affecting the energy budget, and it's mainly clouds over the oceans that has the largest response. Thank you.